I'm Charles Dillard with Amphenol Broadband Solutions. Welcome to our Fiber 201 training series. In this 5-part series, we will dive a little deeper into fiber optics. In this training today, we will be discussing fiber math. So as you go through this training, the chat will be open. So if you have any questions, feel free to put those in the questions section, and I will address them at the end of this training. So let's get started. Fiber optic math is essential for understanding not only fiber design, but also how to maintain a reliable fiber optic network. It enables technicians and engineers to ensure that optical signal can travel the required distances without impairment. This training is broken into 2 parts, fiber calculation and fiber math design. So let's take a look at a few terms and math calculation that we will discuss in this training. First, we will talk about powers of 10. And logarithms and how they relate to one another. We will understand the differences between dB, milliwatt, and dBm. And finally, identify the definition of power budget and how fiber math is used to calculate link loss. Powers of 10 is a way to express very large numbers or extremely small numbers in a compact and easy to calculate manner. Instead of writing numbers with dozens of zeros, powers of 10 allow us to compress them. When we say powers of 10, we mean numbers in the form 10 to the nth power. Base is the number being multiplied by itself. In powers of 10, the base will always be 10. N represent the exponent or power. So exponent answers the question, how many times is 10 multiplied by itself? Or how many times do we divide in case of negative numbers? Powers of 10 describe numbers in exponential form. 10 to the second power is also called 10 squared and is equal to 10 times 10 or 100. Also, the number of zeros after the 1 is same as the number of the exponent. 10 to the third power is also called 10 cubed and is equal to 10 times 10 times 10 or 1000 with 3 zeros to the right. 10 to the sixth power is 10 times itself 6 times and equal to 1 million with 6 zeros to the right. And finally, 10 to the ninth power is 10 times itself 9 times and is equal to 1 billion with 9 zeros to the right. So instead of writing out 1 with 9 zeros, we can simply write 10 to the ninth power. Numbers less than 0 can be expressed using negative powers of 10. 10 to the minus 3 equals 0.001 or 1,000th. Notice with negative numbers, the zeros are placed to the left of the 1. 10 to the minus 6 equals 0.00001 or 1 millionth, and 10 to the minus 9 equals 0.0000001 or 1 billionth. Next, let's take a look at logarithms. Optical power spans a huge range. If we use only a linear scale, small numbers will look invisible compared to large ones. Logarithm is the inverse of powers of 10. They actually undo multiplication or division. By using a logarithmic scale, such as dB or dBm, we compress wide ranges of manageable numbers. We can add, subtract dB values instead of multiplying or dividing raw power ratios. It makes relative changes like halves or doubles easy to compare. Remember, with powers of 10, exponent answers the question, how many times is 10 multiplied by itself? However, logarithm is the inverse of powers of 10. It cancels out multiplication. Instead of asking, what is 10 to the nth power, logarithm asks, what exponent or power of 10 is needed to produce that number? A logarithmic scale is a way of plotting or measuring values where each step increases by a multiplication factor, not by simple addition. On a linear scale, every step adds the same amount. Example 1, 2, 3, 4. On a logarithmic scale, every step multiplies by the same factor. Example 1, 10, 100, or 1000. That means the distance between 1 and 10 is the same as the distance between 10 and 100. Even though the difference in value is much larger, each power of 10 corresponds to a plus 10 dB step. Now let's take a look at the difference between dB, milliwatt, and dBm. Technicians and engineers switch between dB, milliwatt, and dBm depending on what they're analyzing. So you can use milliwatt when you actually need to know the actual physical power. For example, is my laser safe? Does the node input exceed its max rating? Use dB when you're describing losses or gains in the system. For example, fiber attenuation is 0.25 dB per kilometer. A 32-way splitter has 17 dB of loss. A connector loses 0.5 dB of signal. Use dBm when you need to calculate whole system from end to end. So for an example, a transmitter has a 17 dBm output. You would then subtract all of your losses in dB and then determine if your receive power at the receiver in dBm is above or below the sensitivity threshold. So what is dB? A dB is also known as decibel. It's a ratio of two power levels or signal strength. It measures relative changes, how much power is lost or gained along the path. For example, a fiber connector might add 0.5 dB of loss, or a splice might add 0.1 dB of loss to an overall link budget. But those values are relative. They don't tell you exact power that is left, only how much it was reduced by. That's why system designers use dB to track attenuation throughout the link. The formula to calculate dB is as follows. For power ratio, the formula is dB equals 10 times log 10 multiplied by the input power divided by the output power. For voltage ratio, the formula is 20 times log 10 multiplied by the voltage input divided by the voltage output. Since this training is focused on fiber optics, we will take a look at the steps to calculate power ratios. If power input equals 100 milliwatts and the power output equals 10, what is the gain or loss in dB? So step 1, use the formula dB equals 10 times log 10 of the input power divided by the output power. Step 2, plug in the values. 10 times log 10 multiplied by 100 milliwatts, which is the input power, divided by 10 milliwatts, which is the output power. This equals to 10 times log 10 multiplied by 10. Step 3, solve the logarithm. Log 10 times 10 equals 1. So dB equals 10 times 1, which equals 10 dB. That means there is a 10 dB gain from 10 milliwatts to 100 milliwatts. In fiber optics, milliwatt is absolute power. This tells us the actual amount of light energy present in fiber. For example, if a transmitter output 20 milliwatt, that is raw physical power being launched. This matters because hardware has strict limits. Transmitters have maximum ratings, receivers can be damaged by too much input, and safety regulation for lasers are based on absolute power level. So let's convert 50 milliwatts to dBm. To do so, the formula is power in dBm equals 10 times log 10 multiplied by the power in milliwatt divided by 1 milliwatt. Step 1, 50 milliwatts is your input power. So you would multiply 10 times log 10 multiplied by 50. Step 2, calculate log 10 times 50. That equals 1.69897. Step 3, multiply 10 times 1.69897. That equals 16.99. And if we round up, 50 milliwatts equals 17 dBm. To bridge these two worlds of dB and milliwatts together, we use dBm. When doing link loss budget, we start with the transmitter's output in dBm. We then subtract the total system loss in dB and finish with a receive power level in dBm. That result can be directly compared to the receiver's sensitivity, which is also specified in dBm. This makes dBm the universal connector between the physical and the relative size of power measurements. dBm measures absolute power level reference to 1 milliwatt. dBm equals 10 times log 10 multiplied by power in milliwatts divided by 1 milliwatt. For example, 0 dBm equals 1 milliwatt. Positive 10 dBm equals 10 milliwatts. Negative 10 dBm equals 0.1 milliwatts. Now let's take a look at all these math terms and formulas and apply it to calculate fiber design. A fiber design worksheet is used to help technicians and engineers design and calculate total loss of a fiber optic link. and compare it to the system's overall power budget. This will help to ensure that the fiber network performs accurately. We begin with input values such as transmitter's output, receiver sensitivity, and power budget. There are two basic types of transmitters used in fiber optic systems: lasers and LEDs. Lasers come in three varieties: long reach, medium reach, and short reach. The purpose of a fiber optic receiver is to see a light source. A receiving device needs a certain minimal amount of light to function within specification. Receivers are rated in terms of required minimum level of received light. Here we are looking at high, medium, and low transmit powers and their respective receiver sensitivity. For example, a short transmitter power might be -3 dBm with a receiver sensitivity of -18 dBm. A power budget is a critical concept in fiber optic design. It refers to the total amount of optical power available to overcome losses in a fiber optic link between a transmitter and a receiver. In simple terms, it tells you whether your signal is strong enough to make it from one end of the fiber to the other. The power budget is calculated using the formula transmitter output in dBm minus the receiver sensitivity in dBm. For example, if the transmitter's output is +3 dBm and the receiver requires at least -28 dBm to function, the power budget is 31 dB. Next, we will look at link loss estimation. This includes fiber length, fiber attenuation, total fiber loss, number of connectors and their loss, the number of splices and their loss, and finally, design safety margin. Here's a table showing some examples of estimation and their losses. We will look at these in greater detail. Fiber attenuation is the natural loss of signal strength over distance due to absorption and scattering in the fiber. This value is typically specified in decibels per kilometer and varies depending on the wavelength used. For example, single-mode fiber has attenuation values of approximately 0.35 dB per kilometer at 1310 nanometers and 0.2 dB kilometers at 1550 nanometers. The fiber cable itself contributes to a large portion of the loss budget. The amount of loss is based on wavelength and distance. In this example, the fiber distance from the transmitter is 9 kilometers at 1310 nanometers. The attenuation at 1310 nanometers is 0.35 dB per kilometer. If we multiply 9 times 0.35, we get a total loss of 3.15. Distance between location and the actual distance of fiber are two different things. You must account for slack that is needed. Additionally, fiber reels are shipped with various lengths. For example, 15,000 feet or 4.5 miles of fiber could be on a reel. So if you had a 20-mile fiber run, you would have to splice the fiber, which add additional loss. Fiber specifications are dBs per kilometer. To convert miles to kilometers, multiply the distance value in miles by 1.60934. For example, if you have a distance of 5 miles, the equivalent distance in kilometers would be 8.0467 kilometers. Splices and connectors also contribute to the loss budget. In this example, there is one splice that loses 0.1 dB and two connectors which lose 0.75 dB. The total loss of the splice and the connectors come to 1.6 dB. Design safety margins ensure the network continues to function reliably over time, even when the following occurs. In cases where connectors get dirty, attenuation due to age of the cable, and any additional splices that are needed. The recommended safety margin may be anywhere from 3 to 6 dB. Finally, we will look at total link loss. Total link loss calculation is the process of estimating the total optical signal loss across a fiber optic link. This calculation is necessary to ensure that the signal arriving at the receiver is within the acceptable power level range for proper operation. Total link loss includes several components: fiber attenuation, connector losses, splice losses, and a design safety margin. So if you had a short-range transmitter with an output of 0.5 milliwatts, you would need to convert that to dBm, which would give you a -3 dBm of signal. And if you subtract your total link loss and include your safety margin, you should have enough power to achieve the minimum sensitivity of your receiver. So in closing, understanding fiber optic math is essential when it comes to designing and maintaining reliable fiber optic networks. Again, this will enable technicians and engineers to ensure that the optical signal can travel the required distances without degradation and that the equipment performs within expected parameters. That concludes our training on fiber math. I see some questions come in, so I'm gonna walk over to my computer and we'll be answering those questions shortly. Make sure I'm muted here. I see that there's a couple of questions that's come in. The first one, with fancy test equipment and design software, is knowing the math necessary? Great question. It is, the short answer, it is important. A lot of the, signal level meters and test equipment that we currently have now, it does a lot of the guesswork for you. For the most part, you can just look at your LED screen and it'll have like, green for good, red for bad. However, it's just going to really give you, the amount of signal or, things based on the parameters that you set in that particular test equipment or meter. So as an example, you can have positive signal at the end of a link. So whether you're talking about fiber or you're talking about, say, coax, but just having positive signal doesn't mean that it's good signal. So an example of it would be like, if you have like a coax drop and for whatever reason, you're losing a lot of signal, you could put a amplifier on it and you can boost up that signal and it will give you a positive number. But that doesn't mean that the signal doesn't have noise associated with it, especially if the signal had any type of issue to begin with. So again, that's where knowing the numbers and the calculation as it relates to fiber kind of come into play, because again, your equipment and your software, they're only as good as the parameters that an individual were to put into it. So you still need to be able to, verify when you're out in the field to say, hey, I'm at this receiver and this is the light level I have. But I know according to my maps, that link is only 20 kilometers. And I know what my output was. Something is not right. So based on formulas and calculation, you can do some numbers in your head, and it will help with like troubleshooting, etc. So again, this training really isn't about having you to memorize a bunch of formulas. However, you need to be able to interpret what those numbers mean when you're leveraging any of those test equipment. So again, it's not necessary for you to memorize all the math, but you need to be aware of how the numbers are generated or calculated. So that way, when you're out in the field or having to troubleshoot it in real time, you kind of have a sense of is what you're looking at on your meter, what it should be based on the design and what your meter is telling you. But then also, if you run the numbers through your head, it all makes sense. So, but great question. We have another question from John. How does the 3 dB rule apply to fiber optics? So with the 3 dB rule, for the ones that have heard it before, you may have heard also the 6 dB rule, whereas 6 dB rule deals more on the voltage side of the house. So when you're talking about coax, but the 3 dB rule simply states that anytime your signal changes by 3 dB, that means that your power, so when we talk about milliwatts, your power has doubled in that case. So for example, if 0 dBm is equal to 1 milliwatt, then as soon as I go from 0 dBm to like 3 dBm, there's a 3 dB increase, then that means my milliwatts has doubled. Now I would have like 2 milliwatts. But also, kind of where that kind of comes into to play is that understanding the difference between like milliwatts and dBm is that there are times where a technician may be like at a fiber node, and they may want to be able to check the amount of power or light coming in, but they may not want to be intrusive. So where you would have to actually take that fiber link, put it into your power meter, and it will tell you, what your dBm is. So one way of doing that is, using a multimeter at that node and seeing, what that level is, and do the conversion in your head. So that way you have the ability to be able to check power by converting it from milliwatts to dBm. So when you think about like the 3 dB rule, anytime there's a 3 dB change in your signal, then that means your power again has doubled. Conversely, the other way, if there's a 3 dB drop in your signal, then that means your power is cut in half. So, if you're an engineer, knowing that I'm going to set up, say, like a fiber to the home design or network, and I have this, this budget that I'm dealing with the distance of the fiber. So, like we talked about earlier, is that if I'm going to put in like an optical splitter, and it's going to be some loss that with that optical splitter. So, for example, if you're going to use a 16-way splitter or a 32 or 64, knowing the math with it of how power doubles or is cut in half, then you have to be able to make up that level somewhere. So, for example, if you're going to go from a 16-way splitter to a 32-way splitter, that doubling of that signal loss is going to cut it in half. So you're going to, lose half of your power, or negative 3 dB. So how would you make that up? So you can have a shorter fiber span. So instead of going, say, 20 kilometers, you can go 10 kilometers. So again, 3 dB rule is really dealing with power and how it relates to power doubling or being cut in half. But it also means that, especially when you start talking about like amplifiers. So when you have an amplifier that has a 10 dB gain or 20 dB gain or 30 dB gain, what it really means is that if you have a certain amount of power coming into your amplifier, how much more is that power working, or the amplifier working on the output? So where a 20 dB gain would mean that it's working 100 times as hard, and a 30 dB gain will mean that it's working 1,000 times as hard. So again, kind of going back with that previous question, is that you don't have to memorize the 3 dB rule from a perspective of doing the math, but being able to identify when your power is being cut in half or when your power is doubling. Because especially from a troubleshooting perspective, if you're familiar with signal as it relates to like amplifiers, if you hit the input of an amplifier with too less of a signal, noise is generated in it. But on the other hand, if you hit a receiver with too much signal, then that's where distortion comes into play, meaning that the original signal is being modified because it's being overdriven. So again, 3 dB rule simply means that the power either is cut in half or it's been doubled based on the dBm and milliwatt relationship. So great question. We have one from Victor. So from a technician's perspective, which math problems are a need to know and which ones are nice to know? Okay. I would say that you want to kind of put them in maybe say 2 different buckets. So, again, your test equipment will, display and maybe say dBm. You may have a piece of safety equipment that may be listed in, say, milliwatts. And understanding that, if I'm looking at, this safety, goggles, for example, and it's rated at a certain, optical level, um, you want to understand, like, as you're dealing with fiber on a day-to-day basis, what lasers are hazardous and what lasers are even more hazardous. So, for example, the stuff that we usually do in our industry, it's pretty safe because the light is contained, say, in the edge of the connector. But if you're using a piece of equipment like a VFL, where there's a red light that is exposed, showing that there's a break or leak in the cable or the fiber, well, that milliwatt is a lot higher. So based on that, you want to be mindful that, hey, I really need to know the math as it relates to the safety equipment, and what glasses I need to use when I'm handling this type of like laser, and especially when you're dealing with um, anything that's requiring more power. As always, from a safety perspective, you want to make sure that you're treating fiber and that laser that is always active, even when you can't see the light itself, because the wavelength that we're dealing with a lot of time is outside of the visible light. So I would say that anything related to understanding safety equipment, you definitely want to make sure that you understand the math and memorize those formulas or equations. The other side of it is that the safety as it relates to equipment. So, for example, I mentioned earlier that when you have a transmitter and a receiver, a transmitter may be have an output of uh, 10 dBm or 20 or whatever it is, but the receiver has a sensitivity level that if you exceed it, you can actually damage that receiver. So, if you're working out in the field, you just want to be mindful of that. Hey, I want to make sure that I never overdrive that receiver. So it's in my best interest to be familiar with what some of those numbers are, and the what levels I should have. Again, this training really isn't about you taking a math test at the end, but from a troubleshooting perspective, you always want to make sure that the levels are where they need to be based on what you're seeing on your test equipment, what you're seeing in the software as they design the maps, your map that are online, or you may still have printed maps. You just want to make sure that the numbers add up with that. So another great question there as it deals with what you need to know versus what you should know. And let's see if there's any additional questions. And it looks like there are no other questions. But while I do have you, I did want to mention that if you're someone that's on the design side of the house, an engineer, as you went through the training today, you probably noticed that there's probably a lot other tests and math that you may have to do. Again, this is just a snapshot of some of the math that goes behind fiber optic designs. Again, so you want to make sure that whatever your company's requirement as far as testing goes, you want to make sure that you're checking for noise and BER, those type of stuff. Reflections is another one that you want to be able to check for. And there's math that goes into those as well. From a design perspective, I know part 2 of this training dealt with taking a fiber optic design and having things placed where they need to be, the optical splitter, the length of the fiber. What you don't want to do is have from a design perspective, a crew go out and place these equipment somewhere random. And now you have to figure out, how do I get the appropriate signal level from one point to the other? And that's where, a lot of time goes into the design of fiber optics, meaning that whether you're using software or you're using, pen and pad to come up with what, these levels should be anticipated when you design it. So again, the more you understand the math that goes into the design, the better you're going to be, not only from a troubleshooting perspective. If you're a fiber technician out in the field and you have to troubleshoot on the stuff after the fact, but as you start to look at your career, and think that, hey, maybe I want to get into the designing side of the house, the engineering side of the house. Well, it will be more important to understand the math as you look to kind of extend your career in this industry. So the more you know on the front end, the better you're going to be later on. So with the math. So again, I just want to check there aren't any more questions. So definitely want to thank everyone for attending this training on fiber math. As a reminder, this is part of the Fiber 201 training series. So there's going to be 4 more trainings similar to this. The next one, I think, is going to be in 2 weeks, November the 19th, and it's going to be on fiber test equipment. And with those, it's going to talk about, the difference between like OTDRs and BFL and power meters, and some of the calibration that goes into it, and the settings of, setting the appropriate wavelengths, etc. So be on the lookout for that. If you're not currently following us on, say, like LinkedIn, definitely be sure to follow Amphenol Broadband Solutions. We release a ton of information, not only on our products, but the trainings that we offer. Also, check out our YouTube channel. There's more information on fiber, and there's our Fiber 101 series that talks about the theory of fiber, fiber to the home setup, the difference between the different types of connectors and the different types of cables, single mode and multi-mode. So definitely check us out on YouTube. And with that, want to appreciate everyone for joining today, and we will see you on the next one. Thanks, everybody.